People, I promise. This is the last video I'm recording. Really expecting them to be truly useful to you in understanding all of these concepts that we've been studying up to now. This last exercise related to the physical properties in a comparative manner of chemical compounds. And we're particularly talking once again about the boiling points. We have these two compounds, the methanol, the smallest possible aldehyde that we might be finding, a very toxic compound which is used as a solvent in many everyday use compounds. We should be reading the labels of the different substances that we use in order to check for the presence of it. I'm saying this is the methanol as its UPAC name. Stock or common name, this is formol or formaldehyde. And we are comparing this structure to the structure of this other also extremely toxic compound, the methanol, UPAC name, or wood alcohol, methyl alcohol. We had said also toxic, responsible of causing blindness when you get into contact with this. And remember that we find this methanol as a contaminant many times in beverages that are sold as very, very cheap types of alcohols. Okay. When thinking about the physical properties, we have to use these three criteria, which are the molecular weight or molecular mass of the compound. We're thinking of the presence or absence of functional groups responsible of either forming hydrogen bonds, or if it's the case that we're thinking about a hydrocarbon with a very low electronegativity difference, then we're thinking about van der Waals forces in a summarized manner. And the last criterion, thinking about steric hindrance. The word steric hindrance sounds a little complicated, but this is very simply related to having a linear or a branched structure. And remember that we are meant to use the three criteria, expecting that the three of them will be useful in explaining why one of the compounds has a higher or lower boiling point, or if it's the case that we're talking about the state of matter in which the compound is, we are expecting the three of the criterion to explaining why one is a gas and the other a liquid, and so forth. But the most important issue about these three criteria is that it might be that only one of the three could be really useful in justifying the physical property. I'm a little tired, you can tell. Okay, so then, let's see. Molecular weight of the CHOH compared to CH3OH. In this structure, you have one carbon, two hydrogens, one O. In the alcohol, you have one carbon, four hydrogens, and an oxygen, which weighs more, even more than the carbon. Do I really need to make the calculations in order to have the molecular weight? Don't think so. If the carbon weighs 12 and the oxygen weighs 16, yes, of course, this alcohol has a higher molecular weight as compared to the aldehyde. What does the theory tell us about having a higher molecular weight? We've learned that when having a higher molecular weight, you are expected to have a higher boiling point. And if we check the information on the chart, yes, we see that we are expecting the alcohol to boil at 64.7 degrees, much higher than the minus 19 degrees at which this solvent will be boiled. So at least up to this point, this criterion is being useful to justify that the methanol is to have a higher boiling point. Moving on, second criterion. This is taking a little long. Okay, there we are. Thinking about functional groups in the structure that could be forming, as I said a while ago, either hydrogen bonds or van der Waals forces. We learned both in our biology course and during our chemistry course that hydrogen bonds are stronger, have a more energy as compared to the weak van der Waals forces. And so then, let's analyze our structure. Here I'm sketching out the structure of my aldehyde with its carbonyl group. And here I'm sketching out the structure of my alcohol. The question here is, which of the two is capable, if any, of forming hydrogen bonds? Going back into all of this theory, when you have a big electronegativity difference, an electronegativity difference of around 1.4, then you are thinking of chances of forming hydrogen bonds. And also recalling that hydrogen bonds are formed when you have a relatively positive hydrogen making bonds to a relatively negative oxygen or to a relatively negative nitrogen. More than clear. For the alcohol, sorry, I don't want it to circle the carbon. I'm only interested in circling and erasing the whole structure. Okay. COH. You have the hydroxyl group, which we've learned is responsible for forming hydrogen bonds. Let's check the structure of the aldehyde. The aldehyde with this double bond to the O has no OH bonds. So the aldehyde cannot form hydrogen bonds. Conclusion. It's the alcohol with its hydrogen bonds, the one that can be forming these attractive forces which make the compound have a higher boiling point as compared to the minus 19 degrees at which the solvent methanol would be boiling. In this case, up to where we're standing, two of the criteria have been used to justify that the methanol will be having a higher boiling point. Last, what about steric hindrance? If we were using our molecular models, you would be having the carbon atom in the methanol making a short in length double bond with the oxygen, making two bonds with the hydrogens. And this compared to a carbon atom forming three single bonds here with the hydrogen, a single bond with an oxygen. Look at the length of my double bond here and my single bond here, forming a bond at the same time with a hydrogen. Up to you to what you're seeing here in my sketch. Which one of the two structures seems to have a more linear structure? I'm expecting you to answer that it's the alcohol that has a more linear structure. If you agree, then with me, and having the background about the linear compared to branched structures, we know that linear structures have the chance of forming, in this particular case, both physical attractions of the type van der Waals forces for the section where you have this CH, making attractions with this CH, this hydrogen feeling some attraction to this carbon. At the same time, this hydrogen possibly feeling attraction to this hydrogen, did I say? Making a physical attraction to this carbon and so forth. This is van der Waals forces. And at the same time, you have to the right, of this carbon, the OH, this H, feeling attraction for this O, this H, feeling attraction for this O. How many physical attractions can you have for the methanol? I repeat, you're not only having the hydrogen bonds, but you're having the van der Waals forces. And so therefore, which of the two compounds should be having a higher boiling point? Yes, of course, the correct answer is the alcohol. And so, as a conclusion, because of the three criteria having justified that the alcohol is the one that should be having a higher boiling point, well, it's the alcohol that has a higher boiling point as compared to our aldehyde. And that's it, guys. I really hope all of my videos will be of a great help to you all. Thank you and see you on Friday. Bye-bye.